Hello, my name is Westfahl, and I'm here to tell you more about the Brazilian Synchrotron Light Laboratory and its new light source, Sirius. Before I start, I would like to introduce you to the Center for Research in Energy and Materials. This is a non-profit organization working under contract with the Brazilian Ministry of Science, Technology and Innovations, and is responsible for operating 4 national labs in our campus. The first lab, LNLS, is the lab that gave origin to this campus, and it was responsible for operating over several years the first synchrotron light source in Latin America, UVX, that was shut down last year and gave place to Sirius, the new Brazilian light source that I'm going to show you more about in this presentation. The lab for nanosciences and nanotechnology is LN Bio, and it is one of the leading facilities for structural and molecular biology, and they work in drug development and repurposing of drugs, and also on the development of drugs by using molecules from our biodiversity, and they are strong users of the synchrotron in bioimaging and structural biology. Next is the National Lab for Nanoscience and Technology. It's one of the most comprehensive labs in nanoscience and nanotechnology in Latin America, and it also hosts a large park of electron microscopes, including a cryo-electron microscope for structural biology, and that is also one of the most advanced in the country. Next is the National Lab for Biorenewables, and they are responsible for developing microbial platforms for the production of biorenewables on industrial scale. And they study microorganisms and biomass in the atomic molecular scale all the way to the industrial processes. These 4 national labs then compose CNBM, which is a national laboratory for research in energy and materials. So before I start showing you the Sirius, let me introduce you to some of the greatest advantages of diffraction limited storage rings. So one of the key aspects, and that was one of the key aspects of optimization for Sirius, is the high coherence fraction of the radiation. So any source we can extract a coherent fraction. That means a fraction of the radiation that maintains the information of the wavefront. And for Sirius, the synchrotron was optimized to produce the largest fraction possible for coherent radiation, and we have more than 50% of coherent radiation in soft X-rays and above 10% in tender X-rays, and this is a common characteristic for 4th generation synchrotron light sources that were optimized for that. And this allows us to do faster coherent diffraction imaging. It is one of the most popular high-resolution imaging techniques for 3D imaging with high contrast used in new synchrotrons. And also is this kind of coherence allows us to extract very high resolution from the diffraction gratings, and for experiments like inelastic scattering that I'm going to tell you more about. So these are just 2 extreme examples, one for coherent diffraction imaging that you see on the left, done in the APS, the Advanced Photon Source in Argonne, Illinois, in the United States. And that's an example also on your right, is the example of an elastic X-ray scattering, where we can use X-ray to probe elementary excitations of matter, collective excitations, magnons by magnons, and we can use that for extracting characteristic of quantum fluctuations in samples. Also, due to the small beam and the in concentration in diffraction limited storage rings, like Sirius, we can use in the future we'll be able to use faster elastic scanning probes for instance, for probing magnetic materials by scanning the electron beam in the source. That would allow us to do scanning probe imaging and change modes of polarization. As well, another characteristic is it's resultant from the low emittance of these diffraction limited storage rings, is the fact that you can concentrate beams into small scales and micro and nano beams with small divergences. That means you can do diffraction with large working distances, small divergences, and use environments like environments for extreme high fields and extreme temperatures, like the ones I'm going to show you in my presentation in one of the beamlines that will start operation. So this kind of characteristic beam allows large working distances for in situ measurements, low divergence for nano diffraction, like we will have in one of the beamlines, and large focal depth of plane illumination, like we have in the coherent diffraction imaging. So this allows us to do this kind of mapping that was done in other third generation synchrotrons, where the crystallinity of a very tiny grain of a catalyst was mapped with a nanometer resolution using diffraction as the main contrast for the image. So these kinds of characteristics allows us to do completely new kind of science in these diffraction limited storage rings, as Sirius will be. This project started many years ago, and it was back in 2012 that the project was moved into the status with a new technology called multi-band achromat. That was back in 2013, as this article was showing, was an emerging technology for synchrotron radiation, and it was being planned to use for the upgrade of ESRF, this is European synchrotron, and was also in construction at Max 4 in Lund. The first actually fourth generation synchrotron started operating in Sweden, and it was also planned for two upgrades or other upgrades. Nowadays there are several upgrades all throughout the United States and America and Asia, and for fourth generation synchrotrons. But back in 2013 we were starting the construction and development of this new technology for the synchrotron, and when we look at the development of our synchrotron back in 2014, we were basically in a playing ground, and in the early 2015 is when the construction started. And so you can see an evolution of this construction that back in the end of 2018 was the civil construction was almost ready, and that's when we started the installation of the storage ring. In this next video, what you see is a time lapse for this construction. So basically now we are looking inside the storage ring, and what you see is the placement of the magnets that make the storage ring and the booster, the other synchrotron that raises the energy of the electrons up to the nominal energy that is stored in the storage ring. So in between mid 2018 and mid 2019, we had this installation and started the commissioning. So if you see now the status, you can see the LINAC, the linear accelerator, where the beam starts being accelerated from to up to 150 mega electron volts, and goes into the booster that brings the energy to 3 giga electron volts. And as this energy of the electron beam is ramped up, is boosted, then it goes into the storage ring. So what you see in here is the movie inside the storage ring. So the electrons that are stored in this larger accelerator is about 530 meters of circumference, and the electrons are stored in these ultra high vacuum chambers that go through these magnets and through the radio frequency acceleration, and they are stored at 3 giga electron volts to produce radiation to the beamlines that receive from this internal part. So what we see here is the front end that connects this internal structure of the accelerator to the external part of the lab where radiation is used in the beamlines. So now we are crossing from the inside of the storage ring to the outside of the storage ring, and before we see all the beamlines that are in their programs, I'll give you an example, just an overview of all the systems that will be available. That's the plan for the next 3 years, to installation of different beamlines for different purposes. The first 2 phases of beamlines will cover different techniques. The first phase, what we call phase 1A, will cover from protein crystallography to inelastic X-ray scattering. So what we have is MANACÁ in the first phase, phase 1A, is an X-ray beamline that works in the range of 5 to 20 keV and is dedicated to serial crystallography, protein crystallography, from using microbeam, the current station, and another future station that we use a submicron beam for liquid jets with protein crystals. CATERETê Beamline is a coherent diffraction imaging and X-ray photon correlation spectroscopy beamline that will work in the range of 3 to 24 kiloelectronvolts. The EMA Beamline, it's a beamline dedicated to analyzing materials under extreme conditions of high magnetic fields and high temperatures or even very low temperatures, and it will work in the 3 to 35 kiloelectronvolt energy range. CARNAÚBA is our nanoprobe beamline. It will work in the 2 to 15 kiloelectronvolt range, so it's a tender X-ray beamline, and we'll work with multiple techniques from X-ray emission, optical luminescence to X-ray diffraction, X-ray fluorescence, so different probes in the same beamline working with nano beams. It has two stations, nanoprobe station and a submicro probe station. That is the first one to be installed. The MOGNO Beamline is the zoom tomography, so it's our highest energy beamline in the first phase, phase 1A. It will work with three different energies, 20, 40, 70 kiloelectronvolts, and is dedicated to zoom-in tomography. So it's a kind of technique that we use a cone beam, and we can work either with low resolution or very high resolutions. Finally, for phase 1A is the EP beamline. It's a beamline dedicated to ambient pressure resonant inelastic X-ray scattering and near ambient pressure XPS. Next beamlines are in construction are the phase 1B beamlines. These beamlines will be covering different techniques from small angle X-ray scattering like Sapucaia to X-ray powder diffraction like Pineda, or X-ray absorption and fluorescence spectroscopy, Quachi. The pair distribution function analysis also will be covered in the Jatobá beamline that will work with a high energy beam, also like MOGNO. Sabiá beamline is also under construction, so it's a beamline that will cover different aspects of magnetism from XMCD to photoelectron emission microscopy. The SAPE beamline is working in the UV range from 6 to 70 eV. It's a micro ARPES, angular result photoemission beam spectroscopy beamline. The CEDRO beamline will work in the intermediate range of UV, low energy UV, so from 3 to 10 electron volts. And the first experimental station is dedicated to circular radiation, circular dichroism. And the Imbuya beamline, our lowest energy range beamline, that will work in the infrared for different techniques like nano to micro FTIR. Now I'll give you a tour for the beamlines, and I hope you to show some of the advances to a movie that we recorded. So I'll start with the soft and biological matter division. This division, as I said, is basically coordinating the efforts in between beamlines that can be connected with different soft matter and biological aspects of synchrotron measurement, starting with CATERETê, which is a CDI beamline. It works with plane wave CDI. We expect to have the first 3D structure of cells with this beamline soon. Sapucaia beamline is a small angle scattering dedicated, so both of them are small angle scattering beamline, but we'll leave the coherent program into CATERETê and the conventional small angle scattering into Sapucaia. The Imbuya, the infrared beamline, it was basically transferred from UVX with micro and nano FTIR. CEDRO is the new beamline, is one of the new beamlines that uses the UV spectrum for synchrotron radiation circular dichroism. There is a strong demand especially from the biophysics community for this technique. And MANACÁ, which is the first one that started operating for protein crystallography. What I'll give you now is a tour over these first two beamlines that the ones are being assembled. So what you see now is a movie in the interior, the installation of the first undulator in this beamline, the installation of the last optical elements. This was already during the COVID. Now what you see is the first beam of MANACÁ, and it was a very challenging to have this beamline coming up. And what you see now, it's the interior of the experimental hutch, and we have one mirror, the horizontal focalization mirror, and at the sample position you see the sample stage, the detector. We are still using the detector from the previous protein crystallography beamline, which will later be replaced by the in-house development. And what we see now is a video of the activities of commissioning, all done online. I think it's the first time it was done in a synchrotron. So most of the people, the employees, were at home and connected with a couple of people here on site. And it was a very exciting way of doing commissioning. We could tell that the results were coming up and people were cheering from their homes and accessing instruments. And we could even bring up to speed the beamline for the first measurements. And what you see now is the first crystal to be measured and the first crystal structure deposited for a COVID structure. These are the first users also with scientific themes connected to COVID. That was one of the things that we started opening the beamline for. So there was a major task force in the country for, in the ministry for bringing science up to speed against the coronavirus. And this beamline coming online was one of these efforts that we've made to help the research in COVID. Next, we have the CATERETê Beamline. What we'll see now is the first hutch, is the hutch where we have the first mirror, the horizontal focusing mirror. Then we walk this beamline to the second hutch. You'll hear more details about the optics of this beamline and the challenges that we still have. This is one of the long beamlines that has its experimental station and the the scattering flight path, vacuum flight path, in this large extension of the building. Again, the first beam coming to the experimental station in the beamline. This is the experimental station of the beamline. I'm walking you inside the experimental station, and what you see is the connection between the beam coming up to the sample and the scattering path. You see there the helium cryogenic system that cools the sample. This is all in an enclosure. And then next, what you see is the large 30 meters scattering path with this large area detector inside the tunnel. This is an in-vacuum system. The largest built MEDIPIX based detector. So this was a development with the Brazilian industry, and it has around 10 megapixel, and we could see the first coherent diffraction imaging coming to this detector. It was very exciting just a month ago, less than a month ago. And this is the team that was some of the teams that were involved with this beamline. And Florian will show you more results about this beamline and the developments made. Next, so these are the two beamlines of the biological and soft condensed matter division that are under construction and that I took you for a visit. Now I'll take you for a visit at the heterogeneous and hierarchical matter division beamlines. But first, let me introduce what are the beamlines that belong to this division. First is a microtomography beamline working in a cone beam. You'll hear more about this beamline also in the presentations. Then our nanoprobe, the CARNAÚBA Beamline, and the three beamlines basically connected with the measurements of pair distribution functions. Jatobá is a PDF beamline, pair distribution function working with high energies from high energy X-ray scattering. Quachi is the EXAFS beamline, that and Paineira is the powder diffraction beamline. So basically all do different ranges of measurements of pair distribution functions and crystallographic structures. The first two beamlines to be that are being installed are MOGNO and CARNAÚBA, and I'll take you now for a tour around these two beamlines. The first one is the MOGNO Beamline.
this was the first, in the end of last year, we installed this first hutch, and we used this first hutch for the first wide beam measurements that were very important for the project. This is the very first micro CT that we did in the Beamline. That not only this was good for the image of the project, but also allowed us to debug and commission several other systems, from the storage ring to this, all the way to the computing systems. And this the second hutch, the experimental hutch, where we will have the cone beam, has just been installed, and we'll have now the instruments coming to this point. And what you see here is the large tunnel that we are installing this this carriage that brings the sample along the cone beam to change magnification of the measurement. This is the control room of the Beamline, has just been installed, and now we'll have continuing the installation of the other components for this Beamline. And now I'll bring you to CARNAÚBA Beamline. This tour now we start also in the first optical hutch. What we see is an old picture of the installation of the first mirror and the baking of the first components. This first mirror is a cryogenic cooled mirror. It's very challenging. It's a big horizontal focusing mirror that has several systems for cryogenic cooling. And you can see in detail here the way the mirror is clamped and cooled, and this has been tested, and it's currently being commissioned. We just had the first beam in this Beamline, and what you see now is the flight path from the first optical hutch to the second optical hutch, where we have secondary slits for the secondary focusing and beam monitor system. And this long path brings us to the last three hutches. This is a 150-meter Beamline. What we see is the 4-crystal monochromator that stays in the third hutch. Then what we see now inside is the installation of the first experimental station. This Beamline has two scanning probes. The first one is this sub-micro to nano scanning probe, and this third hutch is for the Sapoti, which is our highest resolution. This is control room of the Beamline, and you'll hear more about this Beamline, but these are the images of the first beam in the first hutch that we had a couple of weeks ago. Finally, I'll bring you to the last Beamlines of our visit that are in the condensed matter and materials science division. So this division coordinates the EMA Beamline, that basically it's a set of techniques from diffraction to X-ray spectroscopy to measure the microscopic states of matter under extreme conditions. This Beamline is combined with a lab for preparing these diamond anvil cells and other infrastructure for preparing experiments for the extreme condition experiments. Sabia Beamline is a Beamline that is coming on a phase 1B. Basically, we have XMCD and PIM in the Beamline, and there's a high focus of the scientific program in magnetism in this Beamline. SAPE Beamline is the second Beamline that was added in the set of phase 1B, and it's basically the ARPIS Beamline. The ARPIS system that was initially planned to go to the IP Beamline to work in this soft X-ray is now transferred to the UV range. This was an old demand from the user, especially to achieve higher resolutions in angle resolved photoemission spectroscopy. So we still be able to do photoemission in the IP Beamline, but now we'll have a UV dedicated ARPIS Beamline. The EP Beamline is the one that I will show you is in this phase, and is dedicated to RICS and XPS. Together with these Beamlines, we have an in situ growth lab that allows us to grow thin films and other infrastructures that I hope to show you along this visit as well. So now I'll bring you to the EMA and the EP Beamline visit. We start with some pictures of the installation of the front end. you can see that in most of the pictures everyone is using Max because there was a lot of activities going on over this last since the beginning of the year. And the optical hutch, what we see now is the quarter wave plate and the monochromator. And then we walk into the experimental station where we have the K-beam mirror. This is the high pressure and the Raman setup just being brought to the inside of the assembled outside in the lab, and we're bringing, this is the KB system for focusing, and the high pressure system with the Raman spectroscopy simultaneous measurement. You hear more about this beamline in one of the presentations, and the other systems for X-ray detectors and diffractometer that belong to the beamline, as will be clear in their presentations. This is the control room, and again the picture of the first beam that happened a couple of weeks ago. We have a lot of activities going on in this beamline, and you hear more about it in the presentations to come. Finally, the EP beamline. This is a beamline that is being assembled. As you see, we have the hutches, and we have several of the components being placed. This is a couple images took it a couple of weeks ago. This is in a more advanced stage now. But what you can see is the spectrometer and several mirror systems in assembly. This small hutch is where the slits are for the two experimental stations are. The monochromator slits, the exits from the PGM. And they bring the beam after the slits to these two experimental stations. The first one is for photoemission, X-ray photoemission, and the last one, where you see the granite floor, is for the X-ray, the RIX spectrometer. So this is being finalized now, and we'll have the spectrometer coming in the next week.
To finish now, I'm going to present some of the developments that we have done along with Sirius. Just two highlights. One, it was the development of a new high stability, dynamical stability double crystal monochromator. We also developed a 4-crystal monochromator, but this was specially, the double crystal was specially designed to work with high-speed energy scans under very high stability conditions. So right now we have two of these monochromators installed in the Beamlines, EMA and MANACÁ Beamline, and they are under commissioning. But this was a long partnership with my partners that we learned a lot from mechatronics aspects of monochromators that we now built into all the devices that we are developing in optomechanic and sample positioning devices for the Beamlines. Another development that was very important in the project it was a new X-ray area detector based on the MEDIPIX chip from CERN. This chip allows photo counting. So here is an example of how this the kind of hybrid pixel area detector works. So we have these PN junctions implanted in pixelized that within 50 microns we can detect X-rays, transfer this pulse, pre-amplify, and compare with, and digitalize per pixel. So this is a photo counting detector, and we use this technology that was developed within the MEDIPIX consortium, this chip, to build our own area detectors for Sirius with the collaboration of a Brazilian company, Pytech, that now is licensed to produce these area detectors. So this was also several years of development, and now we have detectors installed in the Beamline. In particular, you saw the one installed in CATERETê, that is a large area detector. And over the last 5 years, we now have 6 modules like this with 2.4 megapixel. One is a prototype that is used in different Beamlines. The other one is a 4 modules detector that is installed in the CATERETê Beamline, as you see in the picture here. And you can see that the high frame rate of this detector was tested with high-speed rotation wheel with X-ray transmission image. And we could prove that with this large area, with 144 ships, counting almost 10,000 10 million pixels. We can work with a high frame rate that amounts to almost 400 gigabits per second of data transmission. Obviously, for all this infrastructure, we have to rethink our way of providing the synchrotron experiments for the community. So instead of following this conventional way of having in our facilities sample preparation, data acquisition, and pre-data analysis, on Sirius we are trying to extend the support for users from pre-sample characterization and preparation all the way to computing infrastructure for data analysis and modeling. So this is an important aspect of these new fourth generation synchrotrons, because most of the experiments, if successful, will run very fast. So most of the time the users will spend preparing their samples and doing data analysis. The synchrotron experiments will run relatively fast as of today's standards. So providing this kind of infrastructure will be very important for the successful scientific proposals for the synchrotron. So just examples of these sample preparation labs, I'll show you two of them. This is the chemistry lab that is prepared for samples, chemical preparation of samples, and also a thin film growth lab that is right in front of the MicroARPS beamline, and will serve several of the beamlines in the synchrotron, but will allow users to prepare some samples for especially thin films, magnetic films, topological insulators. So we expect to have this kind of infrastructure ready for the users. Also, data analysis will be provided. We have now a data center that is installed and serves the beamlines with 2 petabytes of data storage, a GPU cluster and a CPU cluster, and these were designed along with the detection system to provide the optimal ways of detecting and transmitting data from the detectors and storing and then recovering them for data analysis with the GPU clusters. I think the colleagues that were involved, the IT group that was involved, and the software of production group, and the Eduardo Michelis, the lead of this scientific computing group. This is one of the examples of software development that is being provided by this group for the community, for the users. So this is a renderization software that was we are working with together with NVIDIA in a platform called Index that allows real-time renderization of large 3D images. So as all of these developments that I showed you, an important aspect of the project was the developments that we've done with Brazilian industry. So from accelerator components to beamline components, detectors, hutches, all the vacuum components. So many aspects that allowed us to spend most of the investment of the project in the country, in Brazil, and develop industries that are now producing components for Sirius. So I finish with honoring Professor Ricardo Rodrigues, that was one of the founders of the synchrotron radiation science and engineering in our country. He was the leader of these two machines, the construction of these two accelerators, the UVX and the Sirius accelerator, and left a legacy for this community that now has Sirius soon available for measurements, to basically waiting for the creativity to propose new experiments and to probe new aspects of matter. Thank you very much.